In this session, we'd like to consider the free electron models. So I explained the electron can freely moving inside of metal. So we assume that electrons are free inside of the metals. They don't interact with ions or does not interact with any electrons. But they are infinite potential energy barriers. So electrons are confined inside of the metals. So we can use a particle in a box models. So if you remember the Schrödinger equation, but in this case we should consider 3D, so second derivative, plus equal epsilon. So to satisfy the boundary conditions, you can find A sine n sub x is integers, pi x over L, sine n sub y, pi y over L, sine n sub z, pi z over L. So you can find out the psi is a wave function, and n sub x, n sub y, n sub z are integer. This psi can satisfy the boundary condition. So if you substitute this back to the Schrödinger equation, you can find that the energy is gonna be pi square h bar square n sub x squares plus n sub y square plus n sub z squares over 2m L square. Okay, this is the energy of an electron inside of this box. Okay, this is energy. And n sub x, n sub y, n sub z is our quantum numbers. Then we'd like to find out the density of state, number of dn of quantum state that have the energy in the range of the dE we'd like to find. 3D, but in this case each axis is n sub x, n sub y, and n sub z. Then each point, for example this point, is actually 1, 1, 1. This point corresponds to the single state. You can find the psi wave functions. Psi is a sine pi x over L, sine pi y over L, sine pi z over L. Also, you can find such a point like this point, this point, this point. Also, this you can find many points. So grid point have different value, different n sub x, n sub y, n sub z. So electrons in each grid point. So you can consider the electron in each grid point could have two different spins. So sometimes up or down, you have two spins. The number of state, you can calculate number of state of states. N can be expressed n sub x, n sub y, n sub z have to be the all positive. So you have to multiply the 1 over 8 because n sub x positive, n sub y positive, n sub z is positive. And then volumes, it becomes 4 pi over 3 n sub rs cube. So n sub rs square is n sub x squares plus n sub y square plus n sub z squares. So n sub rs corresponds to the radius from the origin. This corresponds to the volume. So if you count the volumes, it becomes the number of states, number of the grid point you can find. And then you have to multiply 2 because we have a spin, up spin and down spin. So number of state you can calculate pi over 3 n sub rs cube. Okay, so I have explained up to this point. How many states could calculate? So as I explained, the n sub rs squares, this ones, instead of the sum, you can use a n sub rs squares. Now this is exactly equal to this equation. So instead of this ones, you can substitute n sub rs squares. Okay, you have the same equations. So instead of nrs, you can find the energy is a pi squares h bar squares over 2m l squares nrs squares. So from this nrs is square root 2m l over pi h bar e to the 1 over 2. Then you can substitute this here. N becomes 2m 3 over 2 L cube over 3 pi squares h bar cube e to the 3 over 2. So L cube is correspond to the volumes. Then you could find the n number of state. Then GE, density of state, is dn dE, derivative of n with respect to E. Then it becomes 2m 3 over 2 V over 2 pi squares h bar cube e to the 1 over 2. So we discover density of state as a function of E. So we discover this equation, density of state. Then we can find out the electron concentrations. Before that, we need to consider the Fermi-Dirac distributions. At T equals 0, at absolute zero temperatures, the electrons can fill up the lowest available state, but there is not enough room for all of them to go into the lowest state. So at the lowest state, if you consider the lowest state as a one energy state, then this is going to be filled by the electron. Then next electron have to go to the second lowest state. Then this electron is occupied from the lowest energy state up to the E sub F0. So all the energy states are occupied by the electrons. Electrons are forced to move into the higher energy state because the lower energy state has been already occupied by electrons. So at the finite temperatures, lowest energy state are occupied by electrons. Electrons have to move to the higher energy state. But due to the effect of the temperatures, at the higher energy state is going to become these kind of the curves. This is the effect of the temperatures. This distribution function is expressed with this function. When you study the statistical physics, we are going to study the Fermi-Dirac distributions. But at this moment, maybe it might be enough. We consider the T equals 0, absolute zero temperatures. All the energy state are occupied by electrons from the lowest energy state up to the E sub F0. Then we could calculate electron concentration and the Fermi energies. Number of electrons between energy is E to the E plus dE. So we consider this number of the dN is a F sub E is a for each state. how many electrons can occupy times number of state you need to consider G dE. This is number of state. Then we could calculate how many electrons actually occupied energy between the E to the E plus dE. You can substitute all the informations. It becomes 1 over exponential E minus EF over KT plus 1 times 2m 3 over 2 V volume over 2 pi square h bar cubes e to the 1 over 2 dE. So at the T equal 0 temperatures, this part it becomes 1. So dN becomes this quantity 2m 3 over 2 V over 2 pi squares h bar cubes e to the 1 over 2 dE. Then to find out the total number of the electrons, you need to integrate from 0 to the Fermi energy. 2m 3 over 2 V over 2 pi square h cube e to the 1 over 2 dE. Then if you integrate this, it becomes 2m 3 over 2 V over 3 pi squares h bar cube E sub F 3 over 2. So from these equations, you can find out Fermi energy. Energy of the electrons inside of the metal. E sub F. This is the energy of the electrons. 2 over 3 pi 4 over 3 h bar squares over 2m. Number density of the electrons and the power is just 2 over 3. So using this equation, you can find the energy of the electron inside of the metals. So this is exactly equal to this equations. Okay, so this is the end of this session.